So, you think building a real-world AI application is all about picking the latest, coolest model? Well, if you do, you're really only seeing one piece of a much, much bigger puzzle.
Seriously, is an AI app just about the model? That's kind of like saying a skyscraper is just about the fancy penthouse suite. You'd be forgetting the massive foundation and, all the floors underneath that make the whole thing actually work.
All right, let's make this real. Let's say we're building an AI tool for drug discovery researchers. Their job is to stay on top of the very latest scientific papers in their field, which, let me tell you, is a seriously complex and overwhelming task.
Now, to build something like that, we need a blueprint, and that's the AI stack. We're going to start with the foundation, the hardware and the model's brain. Then we'll figure out how to give it the right knowledge, teach it how to actually plan and execute tasks, and then build the part our researcher actually uses. And finally, we'll see why every single one of these layers is just absolutely critical.
Okay, first up, more than a model. Let's take a look at the full blueprint for our intelligent system.
Pretty much every powerful AI system is built on these 5 core layers. You've got the infrastructure, that's the ground it all stands on. The models, that's the engine. The data, that's the fuel. Then orchestration, think of it like the GPS telling it where to go. And finally, the application. That's the dashboard the user actually sees. We're going to build this thing from the bottom up.
So, let's dive into the foundation, the hardware and the brains. This is the absolute bedrock of our entire operation.
First decision, infrastructure. Where does our AI actually live? These massive models need some serious horsepower, specifically GPUs, graphics processing units, which are just perfect for all the heavy math they have to do. And you've got 3 main choices here. You can go on-premise, where you buy and manage all the servers yourself. It gives you total control, but it costs a lot up front. Or you can use the cloud, basically renting that power, which is super flexible and lets you scale up or down. Or especially for early prototypes, you can just run it locally on your own machine. It's great for privacy, but you're probably going to be limited by your laptop's power.
Okay, so once you have a place for your AI to live, you need the brain itself, the model. This is the core reasoning engine that's going to power our whole research tool. And right away, you hit a big fork in the road. Do you go with an open model? It's transparent, you can get under the hood and customize it, but it definitely requires more technical know-how. Or do you go with a proprietary model from one of the big tech companies? They're often incredibly powerful and super easy to use right out of the box, but you have way less control. It can feel a bit like a black box.
But wait, there's more. It doesn't stop there. You also have to think about the model's size. A huge language model might have more raw thinking power, but a smaller one could be way more efficient and actually fit on less powerful hardware. And then there's specialization. Is the model you're looking at really good at reasoning through complex science, or is it better at writing code? Every model has its own unique strengths and weaknesses.
And the amount of choice you have today, it's just staggering. I'm talking over 2 million models available in public catalogs like Hugging Face. Whatever your specific need is, there's a really good chance a model already exists that can help you get started.
All right, part 3, giving your AI knowledge. Because let's face it, a powerful brain is pretty useless if it's completely out of date.
And here's the core problem we have to solve. Models are trained on a snapshot of the internet. That means they all have a knowledge cutoff date. So for our drug discovery tool, which needs to analyze papers published like last week, this is a total deal breaker. The base model just plain doesn't know they exist.
So how do we fix this? We use a technique called Retrieval-Augmented Generation, or RAG. I know it's a fancy term, but it's for a simple, really powerful idea. We're basically going to give the model a cheat sheet. We supplement its built-in, static knowledge with fresh, external information. In our case, all those brand new scientific papers. Here's how it works. First, our researcher asks a question about a new discovery. Then, the system dives into an external database, our library of all the latest papers, and retrieves the most relevant documents. And finally, it hands both the question and those documents to the model, which uses that fresh context to generate a smart, up-to-the-minute answer. It's simple, but incredibly powerful. Okay, so our AI is smart and it's informed. Now for Section 4, teaching your AI to plan. A complex query like summarize the top 3 breakthroughs in gene editing this month, well, that requires more than just a single step.
This is where the orchestration layer comes in. The very first thing the model does is think. It uses its internal reasoning to break down that big, complex request into a series of smaller, manageable tasks. It literally creates a plan of attack.
Then it executes that plan. And this isn't just about writing text. Execution could mean calling other tools, like a search engine to find the right papers, or a special function to pull key data out of a PDF. It's all about actively gathering the pieces it needs.
And finally, and this is the part that is really fascinating, it can review its own work. The model can look at its first draft of an answer, critique it for accuracy or clarity, and then run the whole process again in a kind of feedback loop to improve the final output before our researcher ever sees it. It's like having a tiny peer reviewer built right in.
Okay, we've got all the internal machinery humming along. Now for the final, and maybe most important piece, the user-facing layer. This is all about how our scientist actually interacts with the amazing tool we've just built.
Because at the end of the day, a real person has to use this thing. So what makes a great AI application? Well, first, the interfaces. It's probably more than just typing text in and getting text out. Maybe our researcher wants to upload a chart or a diagram. Second, usability is just critical. Can the user easily tweak the AI's output? And, super important, does the tool show its sources and citations? And finally, integrations. Does our tool play nicely with the other software our researcher is already using every single day?
And that brings us to our conclusion, why the full stack matters. It really is about seeing the whole picture, from the silicon chip all the way up to the pixels on the screen. Here's the bottom line. Every single choice we made along the way, from the hardware we picked at the very beginning to the usability features we added at the end, it all directly impacts the final product. These decisions affect the quality of the answers, the speed of the system, the total cost to run it, and of course, the overall safety and reliability of the tool. They're all connected. So when you understand how all of these layers fit and work together, you can start making smart, practical choices to build AI systems that actually solve real-world problems. The blueprint is clear. The only question left is, what will you build?